This video is a continuation of the previous video on section 12.3, which is about dot product. And then in the last video, I explained the concept of dot product and some of its properties. Then now in this video, I'm going to present a couple of things you could do with dot product. The first one of them is about direction angle and direction cosine. And direction cosine. So let's do with an example first. Let our vector A is 2, 5, 1. Okay. And then now, so it's a vector in 3 dimensions in R3. And this is 2, 5, 1, so it looks kind of like this. So this is our vector A. Okay, then now let alpha, beta, gamma be the angles between the vector A and I, j, k respectively. What does that mean? That means the vector I is essentially the unit vector on the x-axis. So this is vector I. And the vector j is the unit vector on the y-axis. So this is vector j. And the vector k is the unit vector on the z-axis. Then now alpha, beta, gamma are the angles between A and each of those. So that means alpha is this angle. In other words, it's the angle between A and the x-axis, that's alpha. And then beta is this angle here. And gamma is the angle between A and the z-axis, or the vector k. That's gamma, so alpha, beta, gamma. And now, the question is this. Compute alpha, beta, gamma. Well, we already know how to compute the angle between two vectors by using dot product. That's one of the things we did in the last video. So here's the answer. So alpha is the angle between the vector A and the vector I. So by using the formula from the previous video, cosine of the alpha is A dot I divided by the magnitude of A times the magnitude of I. So that's the general formula for cosine alpha, cosine of the angle between two vectors. Then now what's this in this case? Well, remember vector I is just nothing but 1, 0, 0. And if you take the dot product with this vector and the vector A, 2, 5, 1, then you will see that since those two are 0, those two also become 0 after you take the dot product. And what you do is actually, after all, just extract the x component of A. And then this is 2. And then what's the magnitude of A? Well, let's just keep it as magnitude of A. Times the magnitude of I is 1 because it's a unit vector. Remember, a unit vector is a vector with a magnitude 1. So this is just a 2 over A. Then now, this is a 2 divided by, now let's compute the magnitude of A. That's 2 squared plus 5 squared plus 1 squared. And take the square root. And that is equal to 2 divided by root 30. Okay, so that's cosine alpha. And then we could do the same thing with cosine beta. Namely, cosine beta is the angle between the vector A and J. So this is A dot J divided by root A, no root A, sorry, magnitude of A, magnitude of J. And that is, now remember vector J is just 0, 1, 0. So if you take the dot product with this one and this one, what you get is the middle component, 5. So this, and then you get magnitude of A times, once again, the magnitude of J is 1. So this is 5 over the magnitude of A. And that is 5 over root 30. And finally, cosine gamma is A dot K divided by the magnitude of A times magnitude of K. Then now, remember vector K is 0, 0, 1. And if you take the dot product of 0, 0, 1 with this vector here, what you get is the last component, 1. So this is 1 divided by magnitude of A times, of course, the magnitude of K is again 1. And that is equal to 1 over magnitude of A. And that's 1 over root 30. Okay. So therefore, alpha is, in this case, arc cosine of 2 over root 30. Beta is arc cosine of 5 over root 30. And finally, gamma is arc cosine of 1 over root 30. Okay, and then those angles are called direction angles of the vector A, and then their cosines are called direction cosines. So those are those. Namely, here's the definition. Those alpha, beta, gamma are called the direction angles of the vector A in the x direction for alpha and the y direction for beta and the z direction for gamma. Respectively. Then also their cosines are called the direction cosines. Cosine alpha, cosine beta, and cosine gamma are called direction cosines. All right. So in general, here's a formula. In general, given a vector in R3, A1, A2, A3, then cosine alpha is what? Well, remember the way to get cosine alpha is to take the dot product with A with I, but I is 1, 0, 0. And if you take the dot product with 1, 0, 0 with, let's say, this one, what you get is basically the x component. And then moreover, magnitude of I is 1. So therefore, in general, what you get is A1, the x component of the vector A, divided by its magnitude. And the cosine beta is A2 divided by A. So this one, to get this one, you compute J. And J is 0, 1, 0. So if you take the dot product of this with this, what you get is to pick up the middle component, so to speak. And then finally, cosine beta is A3 divided by the magnitude of A. Okay, so that's about direction cosine, direction angles, and direction cosines. So that's the first thing for this video. And now, the other thing I have to cover in this video is the concept of projection. So here is a situation. Given A are two vectors, A and B, with neither of them is 0, A is not 0, and B is 0, B is non-zero. Then, remember what we did last time was that A dot B is the magnitude of A times the magnitude of B and the cosine theta. And then pictorially, it looks like this. Vector A here, and vector B here, and theta is here. And then this part here is the length of the vector here. That's what we did last time, in the last video. And then this vector here is called the projection of the vector B onto A. Projection of B onto A. And then this vector is often denoted by proj, right here, proj AB, projection of B onto A. So therefore, this is actually written as magnitude of A times the magnitude of the projection of the vector B onto A. Okay. Then now, the question is, how do you compute proj A, proj AB? More concretely, how to compute proj AB? Well, we know, okay, now look at this one. From this, we know the magnitude of proj AB is now written as A dot B divided by the magnitude of A. Okay. So here, this is this. Okay. And from this picture, proj AB has the same direction as A. Proj AB and A are parallel to each other. They are pointing to the same direction on the same line. So this one has the same direction as A. What does that mean? Well, this means, what this implies, proj AB is a scalar multiple of the vector A for some scalar. That's the meaning of two vectors parallel to each other. Two vectors are parallel to each other if and only if they have the same, one is a scalar multiple of the other, because if two vectors are pointing to the same direction, that means if by multiplying an appropriate scalar to one of the vectors, you get the other one. So in this case, like vector A and the proj is here. So that means by shrinking A by some appropriate number, you get proj. So scalar A. For some scalar, it's not A, sorry, some scalar C. But let's assume for now that C is positive. C is positive means here the angle is an acute angle. If the angle theta is an obtuse angle, namely bigger than 90 degrees, then actually proj is going to be this way. So in this case, C is going to be negative. You have to multiply negative number. But it's just a small issue. Let's just assume C is bigger than 0. Okay. Then, from this, you will see that the magnitude of proj AB is C times the magnitude of A. And then from this, you will see that C, the constant C, is proj AB. Magnitude divided by the magnitude of A, which is, now, let's use this. We know that the magnitude of the proj is computed as this, and then you further divide that by the magnitude of A. So that means A dot B divided by the magnitude of A times 1 over the magnitude of A. And that is simplified as A dot B divided by the magnitude of A squared. Okay. So that's constant C, and that's this. And then this is going to be plugged into here. So therefore, proj is computed as, so therefore, proj AB is computed as A dot B divided by A squared. So that's a scalar. This entire thing is a scalar times A. Okay, and then this is called a vector projection. And by the way, it is your exercise to convince yourself that even if C is negative, the same argument essentially works. Anyhow, then now, let me just note that, first of all, this proj AB is called the vector projection. Because it's a vector. And its magnitude is called the scalar projection. It's just a terminology. It's called the scalar projection. And then this scalar projection is sometimes denoted by comp AB, and it's called component of B along A, called the component B along the vector A. The reason is this. Basically, the idea of projection is this. Suppose you have a vector A, and then suppose you have a vector B, vector B, and then if you project this down to vector A, and you get the vector, another vector like this, and then the magnitude of this is sort of like a a component of the vector b. And in fact, if you have like another a, like a prime, and then if you do the same thing with a prime, then you get two vectors. One is on a, the other is a prime. And in this way, you could sort of decompose the vector b into those two vectors. And in fact, if you add those two vectors, you get the vector b back. So therefore, this is like a sort of like a relative coordinate system, if you like. And then this part is like a component, and this part is a prime component. But anyway, so that's the rationale for the terminology. But for now, it's just know those words and know how to compute them. Okay, so that's pretty much the end of this video, which is like the continuation of the previous video.